Hey chemists! Today I'll be presenting question 2 from the 2016 AP Chemistry exam. Let's get started. We have a chemical reaction here that reads NaHCO3 plus Hc2H3O2 yields NaC2H3O2 plus H2O plus CO2. The instructions below tell us that a student designs an experiment to study the reaction between NaHCO3 and Hc2H3O2. The reaction is represented by the equation above. The student places 2.24 grams of NaHCO3 in a flask and adds 60 milliliters of 0.875 molar Hc2H3O2. The student observes the formation of bubbles and that the flask gets cooler as the reaction proceeds. The first part of this question asks us to identify the reaction represented above as an acid-base reaction, precipitation reaction, or redox reaction. It also asks us to justify our answers. First, let's take a look at the equation we were given again. Notice what the reactants are. We've got NaHCO3, also known in the trade as sodium bicarbonate, and we've also got Hc2H3O2. Sodium bicarbonate is basic, and Hc2H3O2 is acetic acid, which is acidic. So essentially what we have here is a reaction between an acid and a base. So this is an acid-base reaction. Correctly classifying this reaction will earn you the first point. In order to earn the second point, we must provide the correct justification. One way to go about it is what we just discussed. We've got HCO3-, a base, reacting with Hc2H3O2, an acid. In this case, the acid is donating a proton. This is a correct justification and will earn you the second point, but you could also go about this another way, by process of elimination. If you take a look at the products, you will notice that no solids are being formed. This means that this is not a precipitation reaction. And if you went ahead and wrote the oxidation numbers for all of the elements in this reaction, you would also notice that the oxidation numbers don't change. Therefore, this isn't a redox reaction either. So this would be an acid-base reaction. This is also a correct justification, and writing either of these justifications will earn you the second point for this problem. Next, the problem asks us to identify the limiting reactant. To do this, we must first figure out how many moles of each reactant we have. Here's the equation again. The instructions on the first slide told us that we started off with 2.24 grams of NaHCO3. We take this quantity and we multiply it by 1 over its molar mass, which is 84 grams, and we get 0.0267 moles of NaHCO3. We do the same thing for acetic acid. We start off with 60 milliliters of acetic acid and we multiply it by its concentration, which is 0.875 molar. If you recall, molar is moles over liters, and 1 liter is equal to 1,000 milliliters. After we perform this operation, we get 0.0525 moles of acetic acid. If we take a look at the equation again, we can see that the reactants are reacting in a 1-to-1 ratio. This means that we can directly compare these amounts that we just calculated. We have 0.026 moles of NaHCO3 and 0.0525 moles of Hc2H3O2. Since we have less moles of sodium bicarbonate would be the limiting reactant. Correctly doing the calculations will get you the first point for this problem, and correctly identifying the limiting reactant as sodium bicarbonate will earn you the second points. Next, the student observes that the bubbling is rapid at the beginning of the reaction and gradually slows as the reaction continues. Explain this change in the reaction rate in terms of the collisions between reactant particles. So here's a chart that you might remember from our unit on rates and equilibrium. It shows that as the reaction proceeds, the reactants get consumed. As the concentration of the reactants decreases, collisions between the reactant particles also decrease, resulting in a slower reaction rate, as you can see in the second graph that I've put here. Correctly writing an explanation along these lines will earn you the point for this question. Now we have a question on thermodynamics. The question reads, in thermodynamic terms, a reaction can be driven by enthalpy, entropy, or both. Considering that the flask gets cooler as the reaction proceeds, what drives the chemical reaction between NaHCO3 and Hc2H3O2? Answer by drawing a circle around one of the choices below. Since the question tells us that the flask gets cooler, we know that this reaction is endothermic. Therefore, the reaction is not being driven by enthalpy. It has to be driven by entropy only. Circling this option will get you the point. The second part of this question asks us to justify our selection in terms of delta G. Here's the original equation that we were given again. If you remember from our spontaneity unit, delta G was equal to delta H minus temperature times delta S. And in order for a reaction to be considered thermodynamically favorable, delta G had to be less than 0. Since this reaction is endothermic, the delta H value is positive. So if we want delta G to be negative, delta S has to be a positive number. Therefore, entropy has to increase. Another way that we can think about this problem is to look back at this equation. If you notice, on the reactant side, we have no gases. However, on the product side, we've produced a molecule of gas. Since more moles of gas are being produced, there is an increase in entropy in this reaction. Again, this reaction is being driven by entropy. Writing a justification along these lines will earn you the point for this question. Next, we are asked to draw a Lewis structure. For this, we will go over to the whiteboard, so bear with me. Hey chemists, we've moved over to the whiteboard for part E of this question. The question reads, the HCO3- ion has 3 carbon to oxygen bonds. 2 of the carbon to oxygen bonds have the same length, and the third carbon to oxygen bond is longer than the other 2. The hydrogen atom is bonded to one of the oxygen atoms. In a box below, draw a Lewis electron dot diagram or diagrams for the HCO3- ion that is/are consistent with the given information. First, let's go ahead and calculate the number of valence electrons that are in the ion. We've got 1 valence electron coming from the hydrogen, we've got 4 coming from the carbon, and 6 each from the oxygen atoms, so 3 times 6. If we look up here, the ion also has a negative charge, so we're going to add 1, giving us a grand total of 24 valence electrons. Let's set this information aside for now. Now we can start building our molecule. In HCO3-, carbon would be the central atom. So let's go ahead and move a carbon atom over here. Okay, there we go. The problem tells us that we've got 3 carbon to oxygen bonds, and that one of the hydrogen is bonded to one of the oxygens, not the carbon. 2 of the carbon-oxygen bonds have the same length, and one of them is a different length. This means we've got 2 single CO bonds and 1 double CO bond. So I'm going to start drawing that down here. So we've got 2 single carbon-oxygen bonds and 1 double bond. Here are the single bonds, and last but not least, the double CO bond. Okay, there we go. We've also got a hydrogen that's bonded to one of the oxygens, and I'm just going to put it on one of the oxygens with a single bond. At this point, let's do a quick check to see if we have the correct number of bonds. The hydrogen's got a complete octet, since it only needs 2 valence electrons. The carbon also has a complete octet. So the carbon's got a complete octet, and the hydrogen's got a complete octet. The oxygen here needs 4 valence electrons. The one down here has a single bond, so it's going to need 6 valence electrons, and the one over here needs 4. So 4, 6, 4, giving us 14 plus 1, 2, 3, 4, 5 bonds. Each bond is 2 electrons, so that's 10 electrons, giving us a grand total of 24 valence electrons. Now I'm going to go ahead and fill in the valence electrons for this structure, so I'm going to fill in all the dots, and I'm going to be right back. Now we've got the valence electrons for this diagram, but this diagram isn't complete yet. The HCO3- ion has a charge of -1, and to indicate that, we're going to put brackets around our structure. we go, here's some brackets, and one more on the right. After we put in the brackets, we're going to need to indicate the charge by putting a minus sign outside of the brackets. Drawing this diagram correctly in its entirety will earn you the first point for this question. Now you might be asking yourself, can't this double bond over here go over to this oxygen? And the answer is yes. It lies in something that we learned earlier this year called resonance structures. And if you remember, we indicate resonance structures with a double arrow. And now I'm going to put in the other resonance structure that could work for HCO3 minus. Okay, here we go. There we go. As you can see in this structure, I've put the double bond on the other oxygen. There we go. And if you go back to the problem, there were a lot of clues. So the question told us that 2 of the carbon to oxygen bonds have the same length, and the other bond is longer than the other 2. In the HCO3 minus ion, the double bond is being shared between these 2 oxygen atoms. That means that these oxygen atoms actually have a fractional bond. They have a 1.5 bond. And the single bond on the oxygen up top is actually going to be longer than both of those 2. And in the problem, they also put the word diagram in parentheses. They put the plural form, and they also put the word R in plural. So they really wanted you to realize that this structure had resonance. Recognizing this fact and drawing the second structure to indicate resonance would have gotten you the second point for this question. Okay, welcome back, chemists. Finally, we will tackle the last part of this question. It reads, a student prepares a solution containing equimolar amounts of HC2H3O2 and NaC2H3O2. The pH of this solution is measured to be 4.7. The student adds 2 drops of 3 molar HNO3 and stirs the sample, observing that the pH remains at 4.7. Write a balanced net ionic equation for the reaction between HNO3 and the chemical species in the sample that is responsible for the pH remaining at 4.7. The first thing we have to realize about this question is that it is asking us about a buffer solution. If you recall, a buffer solution is made up of a weak acid and its conjugate base. In this case, the weak acid is HC2H3O2, and the conjugate base is C2H3O2-. In the question, the student adds 2 drops of HNO3. HNO3 is a strong acid, so it's going to dissociate completely into H plus and NO3- ions. And these H plus ions are going to be neutralized by the conjugate base in order to form HC2H3O2. So the correct net ionic equation for this problem would be C2H3O2-, the conjugate base, plus the H plus ions, yielding HC2H3O2. This is not the only correct answer. We can also write this equation another way. We can write it as C2H3O2- plus H3O+. So now instead of hydrogen ions, we have hydronium ions. We're still going to form acetic acid, or HC2H3O2, but we're also going to have a water on the product side. This is also completely fine, and writing either of these equations will get you the point for this question. Okay, that is it for this question. Thank you so much for watching, and I hope that was helpful.